Hi everyone, and welcome back. Today we're going to be continuing our exploration of real analysis and add a very important characterization of functions of real variables. Up to this point we've discussed what does it mean for a function to be continuous, what does it mean for a function to be uniform continuous, Lipschitz continuous, Holder continuous, Holder alpha, and so on. So now what we're going to do is discuss what it means for a function to be Riemann integrable. So what exactly is Riemann integrability? So we're going to begin with a closed and bounded interval of the real numbers. We're going to call this AB. We're going to assume that it's closed and bounded with A less than B, implying that this interval obviously is non-empty. So the first thing that we're going to do to this interval is partition it. So what do we mean by partition? And there are infinitely many partitions one could perform on I, but for an arbitrary partition, we're just going to be calling this partition P. So a partition P is the non-empty disjoint intervals that comprise this union decomposition. So we have x0, x1, union x1, x2, union all the way down to union of xn minus 1, xm. We're going to be referring to this as interval 1, interval 2, interval n. So we have n intervals that comprise the partition of I, with the requirement that A is x0, B is xn, so those are the boundaries of your interval, and then xj is less than xj plus 1, where j ranges from 0 to n minus 1. Right? So every point, x1, they're obviously equal, but if you have two boundary points for your interval, those must be strictly less than each other, just like our interval AB. The next thing that we want to know is what is called the norm of that partition, and we're going to be defining the norm of that partition to be equal to the maximum of the lengths of each of those intervals, right? Now, obviously, you can choose all of those intervals to have the same exact length, which we call a uniform partition of the interval, but they need not be all the same length. You can choose any x that satisfies this criteria, and you get a partition, but the norm of this partition is going to be defined to be equal to the maximum of those distances. So that's not just any norm, that's actually the infinity norm, but we're just going to be referring to it as the norm of the partition. And then lastly, we're going to define what it means to be a tagged partition. So a tagged partition is just a pair, PT, P the partition, and T is a set of what we call tags, where the tags are just points that belong to this interval with the cardinality of T being precisely equal to M. Which means that if you pick a point in this interval, for example, one could hit x2 and I2 and x3 and I3, you cannot pick the same point, especially if it's on the boundary of both of the intervals. For example, x2 is the right boundary of I2 and x2 is the left boundary of I3. You cannot pick x2 in both of them. So you have exactly n distinct tags from that partition. So let's do a quick example of what we mean by a partition of an interval and also what we mean by a tagged partition of that interval. And let's keep things basic, at least for now. So let's assume that our interval I is the closed interval 1, 5. So let's give an example of a partition of I. So the partition of I is going to start on the left, so we're going to have 1, and then you can go up to whatever number you want. For example, let's go up to the number 2. As long as it's less than 5, then we're good. And then we're going to union, so we're going to pick up where we left off with the last one, so 2. And then we're going to go up to some other number, let's say 3.5. And then this is going to go up to another interval, let's say 3.5 to 4.7. And then let's do one more interval. Let's go 4.7 to 5. Right? So is this truly a partition? So the lower boundary is 1, the upper boundary is 5, so at least it covers the entire interval. And we have that 2 is less than 3.5 is less than 4.7, and 1 is less than 2, and 4.7 is less than 5. So this is indeed a partition of I. In particular, we have interval 1, interval 2, interval 3, and interval 4. So let's see if we can figure out what the norm of this partition is. So notice that the length of I1 is just going to be equal to 1. the length of I2 is going to be equal to 1.5. The length of I3 is going to be equal to 4.7 minus 3.5. So that's going to be 1.2. And the length of I4 is just going to be 5 minus 4.7, so we have 0.3. That means the norm of the partition, or the infinity norm, is going to be equal to the maximum of 1, 1.5, 1.2, and 0.3, which obviously is equal to 1.5. And then from here, we can build our tag partition. So the tag partition, and keep in mind, if a partition is not unique, technically a tag partition is not unique either. You can choose any points that are in each of these intervals. Keep in mind, since we have n is equal to 4 intervals, we need 4 tags that are distinct from each other. So pick a point between 1 and 2, and you can choose the boundaries if you want. So we can choose, for example, 1.7. Choose a number between 2 and 3.5. We can choose 3.4. Choose a number between 3.5 and 4.7. I'm going to choose, actually, let's choose 4.7. Let's choose the boundary point. Keep in mind, if you choose the right boundary point for I3, you cannot choose the left boundary point for I4. So as long as you choose some number strictly between 4.7 up to 5, including 5, then life will be good. So we have n is equal to 4 subintervals that partition the set I with a norm of 1.5, and obviously a tag partition giving us these particular tags. And obviously we need to couple that with the partition P. So that's our set of tags T. So that's what we mean in terms of a partition of a closed and bounded interval AB, the norm of that partition, or the infinity norm of that partition, and what we mean by a tagged partition of that interval. So now let's get into the real fun stuff. Let's again take our closed and bounded interval I, and let's assume we have some tag partition TP of I. Then we call the Riemann sum of the function f, which maps the closed interval AB to the set of real numbers associated to this particular tag partition, is given by this finite sum. So keep in mind, if I change my tagged partition, even though my function may still be the same, the associated Riemann sum will be likely different, right? So even if you choose the same exact function f, if you change around your tagged partitions, the Riemann sum may be different, right? And the Riemann sum, which we're going to denote by s subscript tp of f, is going to be equal to the finite sum of, from k is equal to 1 to m, of f of tk, where tk is going to be the tag associated to interval k, and multiplied by the length of that associated interval. You obviously can write this in a couple ways. You could also write this as the sum from k is equal to 1 to n of f of tk times xk minus xk minus 1, the length of interval k if you prefer it that way. All right, so this is what we call a Riemann sum, and you can actually think of this as sort of like a partial sum of some sequence, right? And so it's practically a partial sum of a sequence in disguise. All right, so that's what we call a Riemann sum. Now, what do we mean by a function being Riemann integrable? So this is the star of the show. So let's talk about this. So let's begin by letting f map A to B. We'll map AB to R. And we're going to say it is Riemann integrable. Riemann integrable. And write this as f belongs to the Riemann integrable functions on AB. So it's Riemann integrable on AB if there exists a number L. You can think of this as a limit in the set of real numbers, or a value in the set of real numbers, such that if for all epsilon greater than 0, there exists a delta greater than 0, such that if TP is any tagged partition, keyword here is any, right? So that includes your uniform partitions. The tags could literally be anywhere in that random partition also. So TP is any tag partition of the interval AB, but it has the requirement that the norm of this tag partition is chosen to be arbitrarily small, right? In particular, arbitrarily smaller than that delta. Then, if this is true, then the absolute value of the Riemann sum of f and that number is less than epsilon, right? So you can view this as, as delta gets closer and closer to 0, then that means that the Riemann sum gets closer and closer to L, right? So it's practically a limit in disguise. So we will write this, if it's true, f belongs to the set of Riemann integrable functions on the interval AB, and we're also going to give a new name or a name for this number L. So the value L that this supposedly converges to is called the Riemann integral of f on AB. So that is what a Riemann integral is. So a Riemann integral is the point that this Riemann sum converges to as you make the norm of your partition arbitrarily small, which can also be equivalently viewed as the number of partitions getting arbitrarily large. Because as the number of partitions get arbitrarily large, keep in mind we're covering the same exact length, AB. That means those distances of those subintervals must also be getting arbitrarily small. Now, each of them can get small at different speeds because they could potentially be different size intervals, but all of them will get close to 0 eventually if you increase the number of intervals to infinity. Right? So keep in mind this Riemann sum need not converge, but if it does, in particular converges to L, then we say that f is integrable, or Riemann integrable, on the closed interval AB, and we will say that f belongs to RAB. All right? So that's what a Riemann integral is. So let's introduce our very first theorem for Riemann integrability. And the first theorem says the following. So let's suppose that f is Riemann integrable on the closed interval AB. Then the Riemann integral of f on AB is unique. So if the Riemann integral exists, then the limit Riemann integral is unique. So this isn't surprising. It's practically the same exact result that we had for limits of functions. So let's see if we can give a formal proof for this. So let's assume that L1 and L2 are both Riemann integrals. So they're both Riemann integrals for f on AB. And obviously we're going to be letting epsilon be greater than 0. Then there exist some numbers delta 1 and delta 2, both positive, with the norm of partition 1 less than delta 1, and the norm of partition 2 delta 2. Keep in mind that partitions need not be equal to each other because this has to converge for any partition, any tag partition on those intervals. So if this is the case, then what do we have? Then the distance between S, the tag partition P1 of f, minus L1 must be less than epsilon over 2, epsilon arbitrarily small, so epsilon over 2 arbitrarily small as well. And also the distance between the tag partition 2 of f minus L2 is less than epsilon over 2 as well. All right, so that's what we're assuming to be true about f being Riemann integrable on AB and L1 and L2 both being Riemann integrals of f. So now we need to combine these two into the same world so that this and this are both switched on. So let's assume that delta is equal to the minimum of delta 1 and delta 2. And also let's assume that TP is a tag partition of AB that satisfies the property that the norm of P is less than this delta that is equal to the minimum of delta 1 and delta 2. Any tag partition is fine as long as the norm is arbitrarily small. Then what do we get from that? So what is the distance between L1 and L2? Obviously, if we're going for uniqueness, we need to show that this can be made arbitrarily small, implying equality between the two. So we know that this is going to be equal to, if delta is equal to the minimum of delta 1 and delta 2, what are we going to have? So we're going to have L1 minus S tag partition P of F plus S times tag partition P of F, and then minus L2. And then we can use our triangle inequality trick as usual, and we're going to have that's less than or equal to. Let's write it as STPF minus L1, and then plus STP of F minus L2. Keep in mind, if delta is equal to the minimum of delta 1 and delta 2, then for any partition, because those partitions were arbitrary, that's going to be less than our epsilon over 2, and this is also going to be less than our epsilon over 2. So we're going to have that's going to be less than epsilon over 2 plus epsilon over 2, which is equal to epsilon. And by properties of real numbers, if the distance between L1 and L2 can be arbitrarily made small, then we have that L1 and L2 are going to be equal to each other, implying that if f is integrable on the closed interval AB, then the Riemann integral associated to that limit of Riemann sums is unique. So from here on, now that we have uniqueness, we will write this unique value L to be equal to this fancy little S symbol, lower bound A, lower bound B, so that's the boundaries of our integral, and then for f. So that's the integral of f from A to B, and you may even see some people write L to be equal to the integral from A to B. Some people include the domain value and also some arbitrary length of those subintervals dx, because keep in mind as the partitions get arbitrarily small, that delta x-ish, that xk minus 1 minus xk, is going to get arbitrarily small, right, and get close to 0. And since you practically have multiplication of the height of those little rectangles in your Riemann sum times the length, then obviously multiplication is commutative, and you may even see some people write this as the integral from a to b of dx times fx. And either one of these is perfectly fine, but I'm going to be practically staying with this first one, unless we have to go into some calculus-based calculations with Riemann integrals. So we've done an example of sort of how the general epsilon delta proofs may sort of go about for Riemann integrable functions. Now let's do a couple little computational examples of how actually to construct the value of the Riemann integral, provided that the Riemann integral even exists, i.e. f Riemann integrable on AB. So let's assume that f maps the closed interval AB to R, and let's choose the very nice constant function f of x is equal to 1. Then my claim is that the Riemann integral of f on AB is equal to the length of your overall integral. And let's see if we can provide a nice little proof for this. So the first thing I want to do is sort of analyze my interval. So this is my AB interval. So the first thing that I need to do is partition my interval, and any partition is perfectly okay, because if it is Riemann integral, then the Riemann sum should converge regardless of the tag partition. So what I'm actually going to do is I'm going to choose a uniform tag partition and make all the intervals the same exact length. So I'm going to let h be equal to b minus a over n. So I'm going to have n intervals. So this distance is going to be a plus h, a plus 2h, a plus 3h, and this is going to continue all the way up to b. So let's precisely state what my partition is. So p is going to be equal to a plus h for my first, And then I'm going to choose a plus h and then a plus 2h for my second interval. So we're right there and right there. And then we're going to continue all the way down to a plus n minus 1h up to a plus nh. So the claim here is that this partitions closed interval AB, and obviously a plus h is less than a plus 2h, and a plus 2h is less than inductively a plus n minus 1h. So a plus nh, is that really equal to b? So let's investigate that right quick. So a plus nh will be equal to a plus n times b minus a over m. Those n's cancel, so we're left with a plus b minus a, which is precisely equal to b. So that's actually pretty nice. So if this is the case, then our intervals, let's call it ij, will be equal to a plus j minus 1 times h, and then a plus jh. Here, we're going to take our tags tj to be equal to a plus jh. So we're going to be taking the tags of this partition to be equal to the right boundaries. So a plus h, a plus 2h, all the way down to a plus nh. So that's going to form our tag. That's our partition. That's our tag partition. And now we can form our Riemann sum. So the Riemann sum for tag partition TP of f on AB will be equal to the sum from k is equal to 1 to m. And let's just state the general definition of the Riemann sum just in case you have forgotten it. So we're going to have f of tk, our tags in each of our subintervals, times the distance between xk and xk minus 1, which could potentially be different. But we have chosen that each of those lengths are the same. In particular, each of them are equal to h. And also, the function we're dealing with, f of x, is equal to 1, which means that f of tk will also be equal to 1 for all k. So it's actually kind of boring, but you know, that's subjective, I guess. So what we're going to have is, well, we have a constant which can factor out of our sum, and that's also equal to 1. So we're going to have h times the sum from k is equal to 1 to n of 1. So what's the sum of 1 n times? So that's obviously going to be equal to h times 1 plus 1 plus 1 plus 1, and that's obviously n times. So that's just going to be equal to, so h again is b minus a over m, and then 1 plus 1 plus 1 n times is just equal to m, and our n's are going to cancel, and that's just going to give us b minus a, which is our targeted answer, but keep in mind that's actually not what we have here, because that's the Riemann sum. So we have that the Riemann sum is going to be equal to b minus a. So now we need to find the Riemann integral of f, which is going to be the limit of the Riemann sum. So that means that the integral from a to b of f will be equal to the limit as n goes to infinity of stp. So we're going to increase the number of subintervals, or equivalently, you can take the norm of our partition and send it equal to 0. Either one is perfectly fine. Technically speaking, we don't technically see an n here, but we do see a p here, so sending the partition's norm to 0 is actually a little bit more sound, at least with this notation. So what is that? So we already have the Riemann sum to be equal to b minus a, but b minus a is just a constant and does not change with m. So that's just going to be equal to b minus a, which is the integral that we desire. Now, using the same exact approach and also the same exact partition, but keep in mind it doesn't really matter which partition you use, a very important exercise that I would recommend you try to do is the following. Let's assume that f maps a to b to r with the mapping f of x is equal to x. So this is going to be a little bit more exciting because that f of tk is not just going to vanish magically for all tk, it's actually going to change a little bit. One should be able to show that the Riemann integral from a to b of f is going to exist, and it's going to be equal to 1/2 of b squared minus a squared. And you definitely should have some partial sum relations on hand because you're definitely going to need them for this exercise. Before I get into any semi-fancy theorems of Riemann integrability, I just want to mention a couple algebraic properties of Riemann integrals that you probably are already familiar with from single variable calculus, and they are the following. Let's assume that f and g are both Riemann integrable functions on the closed interval ab. Let's assume that c is an arbitrary real-valued constant. So, a couple of very important things is that if you have a Riemann integrable function and you scale it, it will also be a Riemann integrable function. And if you take any two Riemann integrable functions and add them, you will also get another Riemann integrable function. Moreover, if you have the Riemann integral of CF on AB, technically what you can do is factor out the constant out of the Riemann integral and have C times that limit of Riemann sums, integral AB of f. Similarly speaking, Riemann integrals have the property that the Riemann integral of the sum is equal to the sum of the Riemann integrals, so you can sort of think as Riemann integrals being able to distribute over addition and subtraction. Now, a nice little bounded property in terms of Riemann integrals is the following. If you have a function that's always less than g for all points in that closed and bounded interval, then the Riemann integral of f will also be less than or equal to the Riemann integral of g. So we sort of have a baby squeeze theorem or sandwich theorem for Riemann integrals, which is actually, it can be very useful, right? So another theorem that I want to mention, and the proof of these are actually pretty straightforward as long as you stay close to the definition. So if f is a Riemann integral function, then f is bounded on a b, right? And we had a very similar conclusion when it came to the continuity of functions. So if a function is continuous on a closed and bounded interval, then it was also bounded. But also we have that if a function is Riemann integrable on a closed and bounded interval, then f is also bounded on its range, which is actually pretty interesting. Right. Now, let's get into the more serious theorem when it comes to the boundedness of functions, right? And it says the following. So let's assume that f maps the closed interval ab to R, then the function is Riemann integrable on ab if and only if, right? So here's your super theorem, right? So how do you prove that a function is indeed Riemann integrable? Every time you want to prove something, and if and only if is usually a very important way to go, right? So a function is Riemann integrable on AB if and only if for all epsilon greater than 0, there exist these functions, which I'm going to call u and l, that are both Riemann integrable, AB. So you have to start off with a base class of Riemann integrable functions, u and l, such that L of x is less than or equal to f of x, less than or equal to u of x, right? So we have lower and upper bounds for f for all x in AB. And these functions, u and l, their difference is Riemann integral must be able to be made arbitrarily small, right? So if you can bound your function in between two Riemann integrable functions, and again, if two functions are Riemann integrable, their difference, u minus l, will also be Riemann integrable, then that limit, that Riemann integral, can be made arbitrarily small if, and only if, that function in the middle is Riemann integrable. So now that we have this theorem that provides an if and only if, a bidirectional statement for Riemann integrability, let's see if we can actually walk through an example, or a very famous example, of how to show that a function is indeed Riemann integrable. So how do you show that a function is Riemann integrable? And let's not actually choose a baby function, let's actually choose a very important class of functions. So let's assume that f maps AB to R, and let's also assume that f is continuous on AB. So we're looking at all of the functions that are continuous on a closed and bounded interval, then f is also Riemann integrable on AB. So how do you prove that all continuous functions are Riemann integrable? It's a very strong statement, right? Because we already know several things about continuous functions. So what do we know? So since f is continuous on a closed and bounded interval, so we have function f is continuous on a closed and bounded interval, a closed and bounded interval, then what do we have? Well, that means that f is also uniformly continuous on AB, and we proved that a while ago. So what do we mean by uniform continuous? So that means for all epsilon greater than 0, there exists a delta greater than 0, such that if u and v belong to our domain A and B, with the distance between u and v being arbitrarily small, then the distance between f of u and f of v will be less than some arbitrary number, which I'm going to be calling epsilon divided by b minus a, where that b minus a obviously is motivated towards a simplification that's going to occur a little while down the road. Right? So that's what we get from assuming that the function is defined and continuous on a closed and bounded interval. So now we're trying to show that our continuous function is Riemann integrable, which means we need a partition. So let's suppose that P is the union from k is equal to 1 to m of xk minus 1 xk. xk minus 1 xk. So that's our typical partition, and let's assume this partition is a particular one that has the property that its norm is arbitrarily small, in particular less than r delta. So we have our partition, and we have that the function is continuous on the union of those subintervals. So what does that give us? So since f is continuous, on AB, that means f is also continuous on every subinterval xk minus 1 xk, where k is equal to 1, 2, down to n. So if it's continuous on a full interval, it's continuous on any subinterval of that bigger interval. Okay? So if it's continuous on a bunch of closed and bounded intervals, we've also proved in the past that f attains a minimal and also maximal value in each of those intervals ik. And let's just take a moment to sort of think about why that is the case. So let's assume that we have some function. Let's assume that this is my interval AB. And let's assume that we have some function that's continuous on that interval. Let's partition it with an arbitrary partition. Let's assume that this is my partition, for example. So notice that it attains a maximum on the right boundary at the first interval, a minimum on the second. And then for this next interval, again, a minimum on the left and a maximum on the right. And then for the next one, it appears to be that the maximum is located somewhere in the middle. And then we have that maybe the minimum is also somewhere in there. I don't know, my sketches are super bad. Oh, but this interval looks super trivial. So we have a maximum on the left and a minimum on the right. And that's practically the intermediate value theorem in disguise. Okay? So f always attains a minimum and maximum value on each of these intervals, I1, I2, down to In. Okay, so let's actually define, because we're guaranteed those points exist, let's define the points in each of those subintervals for which they do attain those max and minimum values. So we're going to define uj, and uj is going to be a point in ij, be the point for which f attains its minimal value on ij. So that's the first thing we're going to do. And we're also going to define vj, also belonging to ij, to be the point for which f attains its max value on ij. Now, I'm using the point, but I'm not implying that the point exists. And well, I'm implying that it exists, but I'm not implying that it's unique. It could be a constant function for all we know. And it's possible that uj and vj are equal to each other. But what we're going to do, if they are equal to each other, since we're in a closed interval of r and the left and right endpoints are the same, choose uj and vj to be equal to different if you do have a constant function on that interval, to avoid any issues later on down the road. So once we have that, what are we going to do? Now we're going to define fu of x to be equal to fuj. Keep in mind, uj is just a number, not a variable. So fuj is also just a number as well, right? So fuj is just a number where this point, where these arbitrary points, x, belongs to the interval xj minus 1, xj. The place where uj belongs, right? And let's assume that fu of x is equal to fum if x belongs to the rightmost interval, xm minus 1, xm. And let's similarly define another function, fvx, which is equal to xvj. So that's the function that's going to return the value of the maximum height on each of the intervals. And obviously that's going to be a real number with x belonging to xj minus 1, xj. And let's define fvx to be equal to fvm for x belonging to the interval xm minus 1, xm. And the only reason that we need to sort of have this two-part definition of fu and fv is because I'm defining my left side intervals to be half open, which means we're going to be missing my value on the right-hand side, and we need that to partition my entire world, right? So what type of functions are fu and fv? Well, obviously these are step functions because we're on a closed and bounded interval, and we're truncating the set of integers onto that closed and bounded interval image of our closed and bounded interval domain under our continuous mapping f. So those are definitely step functions. So therefore, what do we get? So by construction, we have that fu of x is going to be less than or equal to fx is less than or equal to fvx, and that's going to be true for all x in a b. Right? So if that's true, that means that f of vx minus f of ux is going to be strictly greater than 0, but potentially greater than or equal to 0 if f of x happens to be a constant function, right? So if that's the case, what do we have? So let's assume that it's not a constant function because it's actually a trivial thing. So let's assume that f of x is not a constant function on AB. It has some change, but keep in mind, we're still assuming it's a continuous function. So if that's the case, then we have that 0 is less than the integral of AB of f of v minus f of u, right? Because f of v minus f of u is positive, so by the little comparison theorem, 0 is less than that integral difference. And what do we mean by the Riemann integral? Well, by definition, that's going to be the sum from k is equal to 1 to m of f of vk minus f of uk. So those are the values of fv and fu for all x. And then we're going to be multiplying that by the lengths of each of those intervals, xk minus 1. So what do we have? So we know that this distance, since f is uniformly continuous, we're going to have that that's going to be strictly less than the sum from k is equal to 1 to n of our epsilon over b minus a. So this is where little epsilon comes into the picture. And then we're going to have xk minus 1. And over here, what do we have? So that's just a constant. So we have epsilon over b minus a. And then we're going to have what? So when k is equal to 1, we're going to have x1 minus x0 plus x2 minus x1 plus all the way down to xn minus xm minus 1. And if you notice, we do have a telescoping series because we have our x1 here, our x1 there, our x2, and then the right side is going to be the next one, and that's going to continue all the way down to that xn minus 1 canceling, and then we're just going to be left with minus x0 xn, which is b minus a in disguise. So that's going to be equal to epsilon over b minus a times b minus a, which, as we already know, is just going to cancel to alpha. Right? So that's what we have here. So if that is the case, then what do we know? So by the sandwich theorem, keep in mind it was an if and only if. So if we can make the distance between these functions, f of v and f of u, to be arbitrarily small, if we can make them arbitrarily small, and we have the property that f of u of x is less than or equal to f of x is less than or equal to f v of x for all x in AB, then the function is Riemann integrable, as long as both of these equations are met, which we proved. Therefore, if f is a continuous function on AB, then we have that f is also Riemann integrable on AB. Or in short, all continuous functions are Riemann integrable. So we've proven that every single continuous function is Riemann integrable on a closed and bounded interval AB. But does a function need to be continuous in order for it to be Riemann integrable? The answer is no. Actually, if you even have just a step function, which can actually be very, very discontinuous because you can have a countable number of discontinuities on AB, then actually step functions are also Riemann integrable as well. Also, keep in mind, if a function is monotone, either increasing, decreasing, need not be strictly, that doesn't necessarily imply continuity either. For example, if we take this little picture here, we have this, picture here, increasing. We can have this picture here, increasing. We can have this picture here, increasing. That's a monotone function that's not continuous on its domain, right? So just because it's a monotone doesn't mean it's continuous. So if it is monotone, then the function is Riemann integrable on the interval a, b. And you're like, well, how can that be the case? Well, practically the proof of that is, you can practically break apart at those little discontinuities and look at those continuous portions, right? So building that argument obviously needs a little upfront construction work, but nonetheless, that's practically the sketch of it. And this principle is actually guided by the next theorem, which is actually very, very useful. So let's see what this says. So let's assume that f maps the closed interval AB to R, and let's assume that C, a real number, is strictly between little a and little b, the boundaries of our interval. Then we have the following two important things. Then the function f is Riemann integrable on the interval AB if and only if the restriction of f on the interval AC is Riemann integrable on AC, and f restricted on the interval CB is Riemann integrable on the interval CB. So if we take this same exact picture, this function on AB is Riemann integrable if and only if the subpieces on each of those intervals is also Riemann integrable, right? So this can be, for example, your C1 and your C2. So if it is Riemann integrable on AB, then it must be integrable on AC1, C1, C2, and C2b, right? So if it's not Riemann integrable on one of those intervals, then it's not Riemann integrable on the entire interval, right? Because we're working with an if and only if statement. Now, if it is Riemann integrable on the little pieces, that obviously implies that it's Riemann integrable on the bigger piece. What is the relationship between those little baby Riemann integrals and the larger Riemann integral? So the second part of this theorem says the following. So if this is true, then the integral from a to b of f, the whole Riemann integral, can be represented as the integral from a to c of f, directly added to the integral from c to b of f. So if you want to find the Riemann integral of the first piece and the second piece added, you just add those baby Riemann integrals together, and that gives it to you. And if you have any notion of areas under curves, then this can be geometrically intuitive, at least to some degree. Right? So that's actually very important, and the theorem proof of that actually isn't super crazy. Now, for our definition for Riemann integrability, there is one slight nuance here. So we assume that the closed interval AB satisfied the property that A is less than B, such that we can always choose a tag in each of those subintervals. So we're going to look at, right quickly before we say goodbye today, we're going to define the following mechanism. So let's assume that F is Riemann integrable on the interval AB, and let's assume that x and y are any points in our closed interval AB with, as usual, x less than y. Then what we're going to do is we're going to define the integral from y to x of f in the following way. Because in the present form of this, if we look at just y to x, y is not less than x, so we're going to get a contradiction. So if you have a lower boundary that is bigger than the upper boundary, we're going to define this to be equal to the opposite of the integral of x to y of f, which is properly defined. Right? So that's how we're going to define that little issue. And from this little definition, you can actually get a very important and actually very useful theorem from the perspective of computational integration. And it says the following. Let's assume that f is Riemann integrable on the interval AB, and let's assume that x, y, and z be any points in the interval AB. Then the following little computational trick is true. The integral from x to y of f will always be equal to the integral from x to z of f plus the integral from z to y of f. Even if x is greater than z, even if z is greater than y, practically what you have here is when you have integrals that have an upper bound on the left and a lower bound on the right, or vice versa, these integrals can practically link together in some sense and form a larger integral on a potentially larger domain. Right? And the proof of this actually comes straight from the definition and a couple of the other properties that we stated before. So these are some of the basics that you definitely should have when working with the theory of Riemann integrability, but we have many other properties to discuss in terms of Riemann integrals that we'll discuss at a later time. So I hope you enjoyed this video, and I'll see you in the next one. Take care.